Natural language is ambiguous and it fails to act as a precise pointer within a continuous visual space.
The coordinates of cognition.
DeepSeek recently came out with a technical paper and discussing about how they are bringing the concept of the chain of thoughts into spatial understanding and visual cognition. And the geeky part of it is that they immediately removed it from GitHub. But there were a lot of people online who were able to uh, take a copy of it, fork it out, and I have been going over the technical paper, and it introduces a very novel approach. There is a fundamental limitation with multimodal large language models, and this is known as the perception gap. The perception gap is when their performance is a lot of times hindered by their inability to see fine grained details within an image. This is solved by taking high resolution crops of an image or employing techniques like vision transformers, which can partition image into patches. However, this does not solve limitation of the reference gap, which is the model's inability to logically reason and accurately point to complex spatial layouts using natural language. Let's take an example of a prompt where we are asking the agent to pick up the object from the platform and move it to the next machine. And then we ask it to rotate it by 90 degrees. But here there is an ambiguity. Which machine should the agent consider? If you look closely, there are two machines to the left. Now, if the agent considers the console in the middle of the room and it forgets to lock it down, this is similar to us or us humans forgetting a name during an intro session. That is because we heard it only once. This ambiguity leads to pointer errors in subsequent reasoning steps and a logical collapse. So, what DeepSeek has done is that they have introduced this concept of thinking with visual primitives. This is similar to the human pointing system. Here, where we use a marker or a crosshair to point to an object within a group. Let me show it with an example. Suppose for this image, I want to find out how many bears are on the ground. The model starts by first locating the bears in the image. These are bounding boxes which refer to each instance. Then it establishes the constraints around it. Like, let's exclude bears which are climbing or on a higher ground. But we should also include bears which are on the ground. Just like humans use a pointing finger to reduce the cognitive load and maintain logical consistency, DeepSeek interleaves these visual primitives into its thought process and mimics the human. So, for example, in this image, the model detects four bounding boxes or four bears, but identifies that one is climbing the tree while three of them are on the ground. So the output is that there are three bears in this image which are on the ground. The model here establishes a standard architecture which is similar to lava, where the input images are processed by a vision transformer to extract the visual features. These are then concatenated with language instructions to form an interleaved sequence of vision language tokens. This is then fed to a LLM to generate responses. The language backbone is instantiated with DeepSeek-V4-Flash, which is a mixture of experts, comprising of 284 billion total parameters, out of which 13 billion are active parameters during inference. There are a lot of things to geek out over here. Like they have claimed that their key value cache compression ratio is more than 7,000 times. That's quite an achievement, especially since the recent TurboQuant paper, which came out from Google. And not only that, they also claim to have average scores which are better than the existing closed source models like Gemini, Claude, Opus, and GPT-5. To solve the cold start problem, the authors have carefully shaped the reward signal. Rule-based checkers act as automated guardrails, preventing infinite loops of bounding boxes being generated, thus shutting down reward hacking before it starts. On the other hand, for dense counting tasks, they have used a smooth penalty curve where near correct predictions are lightly punished, while larger deviations fall off sharply. For maze navigation topology, the moment the model attempts a wall violating transition, all subsequent exploration is causally truncated and heavily penalized, eliminating guesswork entirely. Together, these three mechanisms turn reward shaping from a blunt instrument into something almost surgical. That said, much of this remains behind closed doors for now. Deeper exploration will have to wait until these techniques are open sourced. The authors are also candid about the limitations. The method needs further refinement. The visual primitive mode now has to be triggered explicitly rather than firing automatically. And it's worth holding open the possibility that what we are seeing is less a fully mature product and more a rough research draft, one that still needs to be stress tested for safety and robustness before wider deployment.
But step back from these caveats for a moment. A small open source focused team has produced a model that holds its own against far larger, far better funded competitors. That alone is the headline. Not the benchmark numbers, not the leaderboard position. This is a quiet reminder that thoughtful research, careful reward design, and a willingness to openly share the insight still matter. And this is exactly the kind of work that the rest of the field should do well to emulate.